We are now going to start bringing together everything we've built up to this point. Our rice tables to determine concentrations at equilibrium, working with our equilibrium expressions and constants, rearranging equations to get new equilibrium constants. And let's see what else we have. We've done pH, and then determining the concentrations of our acids and bases at equilibrium. Now we're going to bring all of it together. We're going to add a couple new things today. Actually, the only really new thing that we're going to see is this calculation of the percent ionization of an acid in solution. And I'm going to introduce a new way for you to simplify your work so you're not doing so many quadratic expressions. This week, I'm going to do this a little bit differently. We have only a few slides introducing the concept, and then I'm going to do a couple of separate videos going over distinct problems solving some of these concepts. So let's give it a go. If you remember back in 162, you looked at ionization in solution and the conductivity of solutions. So we talked about things like if something would completely dissociate, how many ions would you have in solution, and therefore how much more conductive would it be? Well, remember, acids and bases, especially strong acids and bases, dissociate considerably in solution, giving us nothing but ions, right? So you'd have like an H3O plus on one side. Well, that's an ion floating around in the solution, like you see in this little beaker here. With this one would be just like a weak acid dissociating with an F minus, and then this is just your picture view of what that looks like. So now let's think about what it means if I have a strong acid and I have very conductive solution. Do you expect the Ka to be smaller, bigger, or dependent on the pH, or no universal trend? Hopefully you came back that Ka would be bigger. So I'm talking about an acid that's solution that's very conductive. That means it has a lot of ions in solution. So that would be something like your strong acid. If I have a lot of ions, I'm going to conduct a lot. And that is something that we can actually measure. So if I use a pH probe, I can use that to determine how much of my acid is in that solution, or by extension, how much base is in that solution. And that's one of the labs that you'll do, I think it's in 2 weeks, where you're going to use pH to determine the concentration of your different ions that are in the solution. So it's a powerful tool. And if you are feeling weak on electrolytes and conductivity, there are a couple of links here. One's to a YouTube video, and the other is to a PhET simulation, so you can kind of see that play out. So the first new thing, or actually one of the only new things that I'm going to show you today, is this concept of percent ionization. And it might sound intimidating, but it's actually rather straightforward. The trickiest part of this is that when we look at the amount ionized, we're looking at the equilibrium concentration. And then it's going to be divided by the initial concentration. So for my ice table, this would be the E line, and this would be my initial line. You want to make sure that you keep those things straight. I think the easier way to think about it is, how many ions did I produce? So if I look at this niacin reaction where I am breaking, remember we're breaking the hydrogen-oxygen bond, so this is the bond that's breaking. And then this hydrogen is going to bond to the lone pairs on that oxygen and give us this H3O plus. So the quantity of this H3O plus of our hydronium then is going to go here. The molarity of the niacin in solution, its initial quantity, is what would go here. So we just want to know how much was made. For our weak acids, you can look at this and you'll see an interesting little trend here. That the more I add, so as I look on the x-axis, the higher the concentration, the lower percent ionization. So if I put just a teeny tiny amount of this niacin in solution, is where I'm going to get the most. So you kind of draw a line down here. The most ionization. And even at that, this is percent ionization, so this is 5%. That means in this solution, I still have 95% of my niacin acid in there. So for our weak acids, it's important to keep track that we are dealing with actual tiny numbers and rather than some large concentrations. And the challenge I would have for you, thinking back to some of the things that we've talked about with like Le Chatelier's principle and whatnot, why do you think as I increase the concentration of how much niacin I have, am I decreasing the amount that is actually going to ionize? And let's talk about that on Wednesday. Now, this is where you're going to be very happy with me, because we are going to introduce an approximation that's going to help eliminate some of that button pushing you do. And this is how can we start ignoring certain parts of our equilibrium expressions when we start calculating things. So specifically, the minus x portion of our rice table. Your book has this quantity. They're like, if you take the initial concentration and divide it by our equilibrium constant, if that number is greater than 500, then it can be ignored. And all I'm going to say to you on that is please don't do that. Because if you think about the link that I posted with examples on why we do our sig figs with our exponents as we do, the same thing applies here. So what you want to do is do your division. So your initial concentration divided by the equilibrium expression. And we want to look at how many sig figs we have in this initial concentration. Not in the K, but in the initial concentration. If there are 2 sig figs, then we would have this 10 to the, would be like 10 to the 2, otherwise known as 100. And then 10 to the 3, otherwise known as 1,000. So if I have something with 3 sig figs in it, then I want this division, this product, to come out being larger than or equal to 1,000. If it's not, I can't ignore it. And let's think about why that is. So let's say I have like 0.10 molar of something. So that would be 2 sig figs. This 0 counts. And if I divide it by a K and I find out that this value here is smaller than the 100, so the 0.10 molar divided by my K. If that is smaller than my 100, what am I saying with that value? Well, look at where this place is. It's in the 100s. So smaller than 100 says that if I have like 0.07, say, is my change, that's significant. But if I have greater than that, so if this is my change, and I subtract that from 0.10, well, I can't very well ignore that change. That's significant, right? So that's where we're looking at for when can we ignore things. But on the other hand, if I have a change in concentration where my x equals like, I don't know, 0.0003 molar, well, if my initial concentration is 0.10 and I subtract this 0.003, my change is beyond what I would see for my sig figs, because I'm still going to be limited to 2 sig figs. So even though there is a small change going on here, the sig figs aren't going to pick that up. But if you stick with the 500, you're going to have times when you're going to discard something and it is going to be significant. I mean, at 4 sig figs, we can have concentrations, and you'll see them in lab where we're like, it's 0.4320. Well, now if my change is in either of any of these decimals, I have to include it because it's going to be significant. If my change is down below here, just any old spot down below my sig figs, then it's not going to be registered. So that's the point of these rules. If my concentration divided by my equilibrium expression, our equilibrium constant, comes out greater than or equal to 10 to the whatever sig figs I have, and typically these are the ones that you're only going to deal with, then we can ignore it. If it is smaller than, then you definitely need to include it. So hopefully that helps. And the next one we're going to do is some examples. We're going to start applying everything I've done here.